Okay, y'all. That was a pretty good quiz, right? We pushed you a little bit. Yeah, a little harder than we've had in the past. So far, we know quite a few different derivatives. I feel like this list of things that we know is starting to get pretty long. You've got the power rule, product rule, quotient rule. It's about to fall apart. Then we've got all these transcendental derivatives that you got to know. Today I'm going to add to this list, okay? That's what we'll do every day pretty much. I'm going to give you some more transcendental derivatives. And specifically, I'm going to give you the rest of the trigonometric derivatives that we haven't gone over yet. So we've gone over sine and cosine. You know the derivative of sine is cosine, and you know the derivative of cosine is negative sine. But we don't know the derivatives of tangent and cotangent and secant and cosecant. So that's what we'll get into today. So first things first, there is a little typo on your notes here. I fixed it for up here, but you might notice that these bottom two say sine and cosine. Let's go ahead and change those to secant and cosecant, because we want to go over all 6 trigonometric derivatives. Okay, so we already know a couple of these, right? We know sine. Okay, what's the derivative of sine? Very good. Cosine?
Negative sine.
Yeah, and the derivative of cosine, you kind of beat me to it there, is the opposite or negative sine. All right, no big deal, right? So what I want to do next is, we're not going to derive each of these 4 because some of them are derived very similarly, but I do want to derive a couple of them. And what I mean by derive is not differentiate, although we are going to differentiate too, but try to figure out what is the derivative, okay? So this first one says, use a quotient rule to find tangent. You might be thinking, well, quotient, there's no division happening here. But tangent, and this is something that you should kind of recall from last year, tangent of x is the same thing as sine divided by cosine. It's just what tangent is. It's the ratio of sine to cosine. So if we think of tangent as sine divided by cosine, the derivative of tangent should be the same as the derivative of sine over cosine. And so now you can see why the quotient rule might be appropriate. Yeah, so let's run through our quotient rule here. So this is going to equal some fraction. All right, so it's going to be the derivative of the top, which is the derivative of sine. So we know that's cosine, times the bottom, which is also cosine. So we have cosine times cosine, which is going to eventually turn into cosine squared, but we'll get to that in a minute. All right, then minus the top, which is sine x, and then times the derivative of the bottom, which is negative sine. So if I multiply this by negative sine, that would be equivalent, instead of saying minus sine times negative sine, we're going to say plus sine times sine. All over the bottom squared, so cosine squared. Okay, so we can clean this up a little bit. I mean, that is the derivative, but we can simplify this quite a bit, because cosine times cosine is cosine squared, right? And sine times sine is sine squared. And we can even simplify this a little bit more if you remember some of your trigonometric identities, or specifically the Pythagorean identity. So you may not remember this from last year, and that's okay. I'll remind you. But maybe I'll just write it out to the side here. Cosine squared plus sine squared. Anyone happen to remember what that equals? It's not tangent squared. It's just 1. And really, the reason why it's 1 is because when you have a right triangle as like a triangle embedded in the unit circle where the hypotenuse is 1, the x-coordinate is cosine, the y-coordinate is sine, so it stands to reason that the Pythagorean theorem would hold here, right? We've got a right triangle, so it makes sense that a squared plus b squared equals c squared. So anyway, that's where that's coming from. And so, yeah, this whole numerator just simplifies to be 1 over cosine squared x. So the derivative of tangent is 1 over cosine squared x, but we can take this one step further. Yeah, because secant is the same as the reciprocal of cosine, or 1 over cosine. So if we have 1 over cosine squared, it's like 1 over cosine times 1 over cosine. That's just going to be secant times secant. So secant squared. And that's about as far as we can go here. So the derivative of tangent is secant squared, and we just proved it using the quotient rule, along with some trig identities, yeah, thrown in the mix. Okay, so that's our derivative for tangent. Now, secant is 1 over cosine, correct? Yeah. Cosine is also 1 over secant. Yeah, they're reciprocals of each other. So let's go back up to our little box here. We'll fill that in. Now, there's a similar proof, and we're not going to go through all the steps because the proof is pretty much the same. You would use quotient rule and simplify just like we did that last one for cotangent. Right? If cotangent is the reciprocal of tangent, then cotangent is cosine over sine instead of sine over cosine. But if you execute the quotient rule on that and simplify, you're going to find that the derivative of cotangent is negative cosecant squared x. I just want you to take a minute to kind of look at the relationship between the derivatives we have up here and just see if you're noticing any patterns or anything. I don't know if we know everything yet, but there seems to be some kind of pattern brewing here. Okay, so now let's find the derivative of secant, and we're going to prove that one too. So secant, as we said before, is the reciprocal of cosine. So we can rewrite secant as 1 over cosine. So yeah, the derivative of secant should be the same as the derivative of 1 over cosine. And how are we going to take the derivative of that? Quotient rule again, yeah. It's almost as if there's a reason we did the quotient rule first here, yeah. Okay, so we'll do the quotient rule here. So we've got the derivative of the top. What's the derivative of 1? Yeah, just 0. So this is going to be 0 times, doesn't really matter, but just for the sake of completeness here, so the bottom's cosine, be 0 times cosine. But you're right, that's just going to all zero out. Minus the top, which is 1, times the derivative of the bottom, which is negative sine. So this is going to turn into plus 1 sine x. All over cosine squared. All right, now trying to simplify this, we're going to do a little kind of algebraic trickery here. But I'm going to rewrite this as, I'm just kind of going to clean up the zeros and the ones here. Sine x over cosine squared x. And I'm going to kind of separate out this fraction a little bit. Yeah, I'm going to split up the cosines in the denominator. Exactly. Yeah, good. So it'd be like 1 over cosine. Oh, I'm used to writing theta there. Times sine over cosine. 1 times sine is sine. Cosine times cosine is cosine squared. So that seems to check out. And then we could simplify each one of those. Well, what does 1 over cosine equal to? Yeah, that's just secant. We already established that. And then we already established what sine over cosine is as well. Tangent. So the derivative of secant is secant times tangent. All right. Now, you know, the reason why I'm going through these proofs with you is because sometimes it's hard to just memorize. You've got so many derivatives to memorize. So it's kind of nice for some of these for you to have like a fallback here, which what I mean by that is like, let's say you're in the middle of the AP test, you just cannot remember the derivative of tangent. We can always derive it like we did here. So you can always kind of come up with it if you don't have the derivative memorized. Now, obviously, it'd be easier if you just memorize them. But just want to give you a little tool here that you can use. Okay, so secant is secant x times tangent x. We're not going to go through the process of proving the cosecant one, but I want you to like look at these 5 derivatives we already have written down, and just let's see if we can use some pattern recognition here, and see if you could guess what the derivative of cosecant is going to be. Stuff. That's exactly what it is. Yeah, very good. Okay, so now before we do anything else, this might be a good time for us to start consolidating our knowledge here. I think we've gone over a lot in this unit, going all the way back to the limit definition of the derivative. So just fill out this next page. Nothing new here, but just to sorry, I'm going to go too fast there. Just to consolidate everything we know on one page. What have we learned over the past like 3 weeks or so? So let's break this down. Yeah, everything we know so far. Yeah, still more to learn, obviously. All right. So the definition of a derivative, like what is a derivative? Well, there's a couple different ways we could write derivative. First of all, we could call it, d over dx of f of x. We could call it dy over dx. We could call it f prime x. All those things mean the same things. They're just different notations for the derivative. And what it equals is that limit. The limit as h approaches 0 of f of x plus h minus f of x all over h. This is really it right here. That's what the derivative is. And you can always find derivatives the long way by doing the algebra with that. Now we have a couple rules that we know. We know the power rule. If we want to differentiate something in the form x to the power of n, this works when x is the base. It does not work if x is the exponent. And that's going to be n times x to the n minus 1. That's the power rule. Then we have a product rule, which tells us how to find the derivative of a product of functions. So that would just be f prime g plus fg prime. The order there doesn't matter. You can put fg prime first if you want. Find this a little easier to say. F prime g plus fg prime. I don't know. Okay, and then we have the quotient rule, which tells us how to divide or find the derivative of an expression where we're dividing 2 different functions. Oh, you know what? I don't want to use f and g here. We're going to use t and b, top and bottom. All right, so it's the top, derivative of the top times the bottom, minus the top times the derivative of the bottom, over b, the bottom squared. Now, notice like the way I'm writing this is a little different than I think how I wrote it originally on the notes, but I wanted to try to be consistent about these two expressions. So you can kind of see the similarities between them. Yeah. Okay, so we're going to write our trig derivatives. So those are all the rules we know. There's one other little bonus rule I guess I'll give you. I'll write that down at the end. So let's write down all of our transcendentals. So hopefully, like before next class, you've got all these memorized. Yeah? And you already have a couple of them memorized. The derivative of sine's cosine. The derivative of cosine is the opposite of sine. And now we've got four more. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant, and I think this is another typo on, I got a little copy paste happy and did not go back and edit it. It's kind of the danger of doing this the first time. So next year will be good. We got secant tangent. So yeah, make sure you correct those little typos on the secant and the cosecant. It says sine and cosine again. So, and then the derivative of cosecant is the opposite of cosecant x times cotangent. So those are all the 6 trig derivatives that we know so far. There's still all the inverse trig functions and their derivatives. We're not quite there yet. Yeah. There's also all, how do you find the derivative of an inverse? Yeah, we haven't talked about that yet. We won't talk about that today or in this unit, but that's coming up later. Yeah. Okay, so the other transcendental derivatives we know is e to the x is just itself, natural log of x. If you differentiate that, you can either write as 1 over x or x to the negative 1. And that's about it. The only other one that, I'll give you a little bonus one, okay, for when you have a constant multiple. Yeah, here's a little bonus rule here. If you have a constant being multiplied by a function and you want to find the derivative of that expression, so let's say it's like 5 times sine x, or 5 times natural log x, or 5 e to the x, or something like that. Doesn't have to be 5, any constant. Then you only have to differentiate the actual function, and the constant will just remain as a coefficient. So for example, like if you had 3 sine x and you want the derivative of that, it would just be 3 cosine x. All right. So that's everything we know so far, right? These are going to be like sort of non-negotiables. You got to know these. All right, so let's do just a little bit of practice. There's no new like real rules or anything. We're still going to be using product rule and quotient rule, but we're just going to throw in some of those trig derivatives, these new ones. So if we want to differentiate something like 4x to the 5th, I'll leave this up so you can get that down, times tangent x, which rule are we going to use for this one? Yeah, product rule. Okay, f prime g plus f g prime. So the derivative of, so here's what I'm going to use as my, well, I don't want to write f because f's already defined here, but these are the two functions. I'll just kind of separate them out like that. So the derivative of 4x to the 5th is going to be 20x to the 4th times the second function, tangent x, plus 4x to the 5th times the derivative of tangent. Now, obviously, at this point, you're probably still looking it up. You don't have it memorized yet. That's okay. But after you do enough practice, hopefully it does get committed to memory that it's secant squared x. Any questions on that one? All right, number 2. All right, let's see. Give you all a second more to write that down. So your job really, as you're going through your homework, is going to be to really commit those 4 new derivatives to memory. And if you struggle with that, I mean, I know I struggle with memorizing things. I really don't like memorizing things. I'd rather just understand it. So, like if it's me, I'm probably just going to derive it every time as opposed to trying to memorize it. But use flashcards. Do something to really force yourself to remember these derivatives. All right, number 2. 9 cosecant x plus 8x to the 5th. So here we don't really have to use product rule. We're gonna have a constant multiple here. That rule doesn't really have a name. Just calling it the constant multiple rule. But here we're just going to differentiate each expression separately. Remember, if you've got a sum or a difference, you don't have to use a special rule to differentiate them. Just take each expression separately and differentiate them. So the derivative of 9 cosecant x would be 9 times the opposite of cosecant x times cotangent x. Plus 40x to the 4th. That's pretty much it. Now, you guys know, hopefully, how I feel about having those negatives like embedded in there. I think it looks a little nicer, and I know you don't really have to do this one little simplifying step, but it definitely looks a lot nicer to pull out that negative. It's just a little cleaner that way. And I'm never going to take off points if you don't do that, but I just can't help myself. Yeah. All right, we got one more. I know there's 2 more on there, but that's because there's a duplicate problem from last time that we don't need to do again. All right, so let's take a look at the next one. Another derivative problem. Now, which rule are we going to use here? Quotient rule. Okay, so let's, out to the side here, make a note of all of the expressions we need to use. The top is 3 secant x. Okay, and my C turned into a parenthesis there. There we go. And then the derivative of that is going to be 3 times secant x tangent x. The bottom function is x squared minus 5, and the derivative of that is 2x. So now we're just going to plug everything into our quotient rule. So the derivative of h is going to be the derivative of the top. So 3 secant x tangent x times the bottom. So I might use brackets here just to really clearly separate it off from that other parenthesis. Minus the top, so 3 secant x times the derivative of the bottom, 2x, all divided by the bottom squared. And do not worry about simplifying this any further. That's good enough for me. Hopefully that's good enough for you too. You might be able to manipulate this a little bit further, but there's really no reason to. And that last problem on your notes is actually the same problem we had at the end of the last notes. I just didn't delete it. So don't worry about that problem. Or if you just really want to see how this worked out, just look at the previous notes. But that's about it for today. I'll go ahead and pass out your homework and